Okay, welcome back to section 4.1. We're going to finish it off by showing you guys how to find the absolute max and min of a function that's constrained to a closed interval. From our previous discussion, we found that it was, okay, visually I can see it, okay, but how do I do it without graphing? Maybe I'm not strong at graphing. You give me a function, I still can do it. Oh yeah, it's pretty straightforward. It's based upon these guys, these particular sorry. I had the wrong pen. These particular theorems here. First one is the extreme value theorem. It says a continuous function, continuous, on a closed interval, there are no surprises. So you've got a closed interval, maybe it's from A to B, and you got a function doing whatever it's doing. And you know that there's some sort of max, maybe there's a min, maybe there's another max here. What's the endpoint? So somewhere along this curve, there's always going to be a max, there's going to be a min. That's the extreme value theorem. The argument is that it's a closed interval, A to B, and it's a continuous function. If you don't have continuity, you might have a picture that looks something like, oh, look at it, I didn't think about that vertical asymptote. It doesn't have a max or a min because it's not continuous. That could be a problem. And the other part of it is closed. If it's not closed, this is going to be weird. But if it's not closed exactly at B, say you go, okay, you can go up to B, but don't be B, meaning it's an open interval, they call it, then your function can be approaching, but you'd think of it as a bullet point, or what do you call it? A bullet hole. Your function is getting closer and closer to it, but never reaches that point. So there's always someone bigger than him, always someone. So it's kind of silly. So you have to close the interval off so that you can achieve the max min, and you have to have continuity so that you have, again, a max min in this case. So that's why continuous and closed interval are important to that. Fermat's theorem is on page 279, and it is proven there, and he does it in an interesting way. I would like to do that maybe someday, but I don't think I've ever done it. I think it's pretty clear that if you've got a function that has a max of some sort, or maybe another function that might even have a cusp and have a minimum, okay? So this guy's got some sort of maximum going on. This guy's got some sort of minimum happening here. Okay, Fermat's theorem is saying this: if it has a local max or min at some value, and f prime of that value exists. In this picture here, nice, smooth, and continuous, f prime of this guy does exist. What he's going to say is that, what does he say? Right here, and I covered it up. He's going to say that the derivative is 0. If f prime exists and you have a local max or min, the derivative is 0. So at this point, if you call this function f and you call this point c, then f prime of c has to be 0 because he's nice and continuous. If you call this function g and you call this maybe d on the x-axis, okay, g prime of d, guess what, does not exist. What the heck are you talking about? Because the slopes are tending towards probably negative infinity from one side, positive infinity from the right-hand side. The derivative doesn't exist. That doesn't mean that the minimum doesn't exist. There is a minimum here when g prime doesn't exist. There is a max here when f prime does exist, but in that case it's 0. Those two places, where a derivative is 0 or where it does not exist, those are interesting places for us when we're looking for maxes and mins and when we're graphing curves. Very interesting. So interesting that they call them critical numbers. A critical number is a number c in the domain of f such that f prime of c is 0 or it does not exist. Okay? Why are those interesting? Well, it allows us to find maxes and mins. Okay? More on that later. Okay, let's move on to the homework. That's what's going on there. The one part of the homework is, can you find critical numbers? And I'll say, yes, we can. Watch us do so. All right, so it says find critical numbers. What are you supposed to do? 1, find f prime. Okay, find the derivative. 2, set, and I think this is up here. Oh, it wasn't. Or is it way up here? It might be up here. Sorry to make you scroll through all this stuff. I guess I didn't write it down, so I'm glad I'm writing it down now. I get confused. Okay, set f prime equal to 0 and solve for, well, x, let's say. 3, find where f prime does not exist. Usually that means you're dividing by 0. Okay, so those many little steps are how you find what? Critical numbers. How you find critical numbers. So let's take this function as an example. F of x is x cubed plus 6x squared minus 15x. We're going to, 1, find the derivative. It's pretty easy. It's a polynomial. We get 3x squared plus 18x minus 15. Step 2, set it equal to 0. Okay, I will. And I solve it. First thing I notice is, how about we divide by 3? I'm looking for, you know what we're doing here right now? We're looking for, where is m tan equal to 0? Remember that clue I gave last video? I said, I wonder where these occur, and I wrote these little horizontal tangent lines on the curve. Yeah, it's where the derivative is 0. I hope that makes sense. What we end up with is we've got x squared plus 6x minus 5 is 0. So therefore, if you can factor, you know what? In this textbook, this guy, he's not so nice. Sometimes they don't factor. I had an example that I was going to do, and it was like, oh, this is horrendous. We should do that another time. Maybe during class, ask homework questions, and we'll do it together in class in Zoom, okay? This is just a video. Let's see, so plus, how does this go? Oh, wait a second. Uh-oh, does this guy not go? Yeah, he can't go. He's got to be positive and negative. So, did I do that one right? I got oh, there's the mistake right there. What did I do there? 2 times 6 is 12. So when I factor that out, I don't have a 6. What do I have? A 4. Oh, thank goodness. Thank goodness. Easy to make mistakes. So now, yeah, we have plus 5 and minus 1. Okay, so the critical numbers so far are x is negative 5 and positive 1. We found those guys. Third question right here is, hey, does this guy ever not exist? F prime is, again, I'll write it correctly this time, 3x squared plus 12x minus 15. And the question is, does it ever divide by 0? Is there any number you cannot plug in? Yeah. F prime exists for all numbers. So there is no place where it does not exist. And so we'll box that up and say, there, we're done. Okay? Let's do this one. Okay, so here comes 8. That's all they ask you to do in this case, is get used to finding critical numbers. Remember, in the back of your mind, critical numbers are where the max and mins are going to be, usually. Okay, now this guy. All right, so 1, what we're going to do is find h prime. Looks like a nasty little chain rule, so what I'll do is I'll write it in a friendlier manner. Okay, to the 1/3 power. So we're going to get 1/3 dropping down, 4 minus x squared, 1/3 minus 1, you're going to leave a minus 2/3 here. I hope you're comfortable with that. And then the chain rule says derive the inside, which turns out to be 0 minus 2x. So I'm going to write this in a friendlier manner because we're looking to see where it's 0 and where it's undefined. Okay? So a good way to write this might be put the negative in front, maybe the 2x upstairs, 3 goes downstairs, and downstairs also, because of the negative 2/3 power, is 4 minus x squared to the positive 2/3 power. There we are so far. You like it? All right. So step 2 would be, and 3, you can do these in whatever order you want. The one step is, where is it 0? And the other is, where is it undefined? Okay? So when you have a rational like this, it's kind of easy. You look at the top. When the top is 0, the derivative is 0. So I'll say it this way. H prime of x equals 0 when the numerator 2x, I don't care about the negative yet, is equal to 0. So obviously there's a critical number, because if I plug in 0 for x, I got 0 for a derivative. I've got a horizontal tangent. Where else? When the denominator is equal to 0, you're dividing by 0 does not exist. So I'll say h prime of x does not exist when, and okay, here we go. Look at this guy inside here. You can kind of see what's happening. If 4 minus x squared is 0, you cube root 0, you get 0. You square 0, you get 0. 3 times 0, it's still 0. So I'll really reason that out and say, hey man, the denominator is 0 when this particular term or expression is 0. Hey, I know how to solve that. You could do it one way, is to go throw him over there, square root both sides. Don't forget, plus minus square root of 4 is 2. So these are a couple more critical numbers. This is where it's not existent. This is where this guy is where it is 0. So we would just say the critical numbers are x is equal to maybe 0 and then plus minus 2. And that is all there is to that. Okay? Finding critical numbers. That was a better example of how crazy it can get. We're running out of time on this video, but that's important. You can pause it and go over it and do the work yourself. Do another one and see how it feels to you. As we go on, the last thing to talk about up here somewhere. Where are you? Here you are. This, I thought I wrote it down somewhere. Finding the absolute max min of a function on a closed interval. So this is the process for doing it. Find the critical numbers find the critical numbers in the interval. So find the derivative, determine where it's undefined, where it's equal to 0. That's how you find critical numbers. So I did write it down and list them. Okay, now to find the absolute max and min, it's going to be kind of straightforward. What you do is you list the critical numbers and the endpoint values in an ordered pair table. That's what I typically do. So for this one, I might go, okay, there's x, and then there's f of x. This is what I mean by an ordered pair table. And you list your critical numbers, and your endpoints, okay? And then all you do is simply compute your function values. Whichever's biggest is your absolute max, whichever's smallest is your absolute min. So remember, we're talking about a closed interval doing whatever it's doing. And you're for sure going to have a max and a min. So the max and min could happen at the endpoints or the critical numbers in between. By the way, when you find critical numbers, not all of them are going to be in the closed interval. So you might be rejecting a few. It's best just to show you how this works. Okay. Here's our first one. Example, f of x is 5 plus 54x minus 2x cubed on the interval 0 to 4. Okay, 1. Find the derivative. So it's a polynomial, life is sweet. Let's see, we get a 54 minus 6x squared. Okay, there's our derivative. That's what we're going to work with. I'll say this right off the bat. Since it's a polynomial, f prime of x exists for all numbers. So you don't have to worry about does not exist in this case, okay? But f prime of x equals 0 when 54 minus 6x squared is 0. I might want to divide out, say, a 6 here. If I do that, we're going to see something better. That's a 9 minus x squared. Aha. So what we're getting is, you can tell x is plus minus 3, right? So these are the critical numbers. But you know what else? These guys are the endpoints. And we have to check those too. The endpoints are x equals 0 and 4. Here's what I like to do to get it right. I go 0 at the top, I go 4 at the bottom, then I look at these numbers to see which ones are in that interval. There's a plus 3, yep, you're there. But then there's a minus 3. He's not in that interval. He's up here somewhere, minus 3. And then, you know what I'm saying? So we don't need to check minus 3. And by check, what I mean by that, the last step you do is you take your function and literally plug each number into this guy to see what you end up with. I don't know if I did. Yeah, okay. I think I did this one. So if I plug in, for example, f of, this guy's going to get an f of 0. You're going to plug in, let me erase this so you can see it better. You're going to plug in x is equal to 0 in this. Then you're going to plug in x equals 3, and then you're going to plug in x equals 4. Into the original function, not the derivative. Make sure you make a table and write f of x. And the numbers I got in this case were, I think these are right, 5, 113, and 93. 113 and 93. Could be a mistake there, but hopefully not. At least you're getting the gist of that. So here's the thing. Okay, we found the critical numbers. Okay, granted, we found, we know what the endpoints are. We rejected minus 3. He was not in the interval. And now we computed their values, and we do a comparison. Which one's biggest, which one's smallest? We get to write the answer. We would say something like this. F has an absolute max of, and I look at the table, which one's biggest? Oh, there it is. F of 3 is equal to 113. And F has an absolute min of, and I look at the table, which one's smallest? Oh, there it is. F of 0 equals 5. And this problem is completely done. Okay, completely done. Okay, so I'm going to go to the next one. You can pause it and look at that, but this next one, you know, that looks familiar because I chose this. I had a different problem going, and it was really messy, so I decided I'm not going to do that. I'm going to steal this guy's derivative, which is here, and it's minus 2x over 3, etc. So on this problem, we'll save some time and remember that h prime of x turned out to be, what is it? Minus 2, what is it? X over 3, and then 4 minus x squared to the 2/3 power. And we found critical numbers. The critical numbers were what? Oh, x is 0, and then plus and minus 2, remember? So that makes our video kind of shorter. So we're going to now continue. But I've now narrowed down this guy's curve. In fact, if you do Desmos on this thing, it looks really funky. Very funky. It looks like a doorknob inverted or something like that. So go ahead and you should do Desmos on this thing for fun. You know, on your computer. But anyway, if you don't have that on a test, so what you do is you go, okay, what I'm going to do is set up my, here's x and here's h of x. And I'm going to put my endpoints. My endpoints, not that you need to list them, but it's really good in notes to do so, are minus 2 and 2 radical 3. So minus 2 up here, way down here, 2 radical 3. And I wonder which ones are in there. Which ones? Which of the critical points? Well, I know that 0 is. He's between those two guys. Negative 2? Oh, yeah, he's actually a critical number. He's also an endpoint. Look at that. So he's definitely just, and you know what else is in there? Let's see. This is 2 times. 2 is also in there, right there, I think, right? Okay, so what we do is we then plug into this function. We're going to plug those numbers in. We're going to plug in x is negative 2. We're going to plug in x is 0. We're going to plug in x is 2. We're going to plug in x is 2 radical 3 for some reason. We're going to plug those numbers in to see what we get. And on a board, you would see me struggle through these numbers, but I think I have them worked out somewhere, or do I? Maybe I don't. Okay. Okay. If I plug in negative 2, h of x, okay, let me write it down. H of x is, again, it is the cube root, not hard, 4 minus x squared. Okay? So if I plug in negative 2, it becomes 4. I got a 0. If I plug in 0, I've got the cube root of 4, whatever that is. So we're talking about the cube root of 4. And that's a positive number. If I plug in 2, likewise 0. And I figured this one out earlier. I chose this guy for a reason. If I plug this guy in, he becomes 12. 4 minus 12 is minus 8. Cube root of minus 8 is actually minus 2. Okay? Last thing before the video ends, we compare these values and we decide which one's the max and which one's the min. So we'll say h has an absolute max of, which one's the biggest? Well, he's the only positive one. It'd be h of 0 is the cube root of 4. There's a winner. That's the max right there. H has an absolute min of, which one's the the smallest? We got 0, 0, but we have negative 2. So h of 2 radical 3 is negative 2 is the min. We didn't hit the critical numbers, did we? Except for the minus 2. So that's how this is done. That's basically, very methodical. Find the critical numbers, put the endpoints up, the critical numbers in that are in the interval, and test to see who has the smallest and biggest value as far as the function value is concerned. That's all she wrote. See you in the next one.